All right, so welcome to STAT 313, lecture 20. So today we'll be discussing the regression problem. And then we will be building on that and we'll be seeing how to compute the confidence interval for that regression problem. So let's get started. All right. So what happens is many times we consider we are interested in getting a relationship between two variables. So the deal is to what is the relationship between, by the way, it's a regression problem. So regression is the name of the chapter. So we are really interested in the relationship between two variables. For example, it can be, say, a student's aptitude test score, and the other variable can be a student's grade in calculus. So, and we are really interested to see the relationship between these two. Now, what we'll be assuming that, well, in most of the times, for not, here we can get a bunch of data for most of the things, but suppose, it's more common to observe the aptitude test score, and maybe we want to predict what would be the student's grade in calculus. So what happens is most of the time, frequently, this is the deal. So one of the variables, one of these variables, say X, is known in advance. The goal is to predict a future random variable y based on the x value. So please note that I'm writing this random variable. So I'm just writing the random variable y, where this variable x are known. Okay, so I'm writing here little x and big Y. Now, now this y is a random variable. So we cannot predict it for certainty. So that, it's a random variable. So that means would be interested, we would be interested to know E of y, or the expected value of y in this case. Okay, that too would be a function of x. So for example, when we studied the, say, if I think this as x, the student's aptitude test score, and if I think this one as y, so of course, so the student's grade in calculus will be somehow dependent. So the expected value of the student's calculus grade will be somehow dependent of his or her aptitude test score. So that means it will be a function of x. Now, we'll be trying to model this. So we'll try to model this. We will try to model y. based on a sample of X, which is given by, say, X1, X2, Xn. So these are observed values. And we are trying to predict Y based on this observed values. Okay, so that's the deal. So now let's see. So the model, denote Y sub I to be the response at X sub I. That means for, if I know X sub I, its a corresponding random variable for Y is Y sub I. And here I is 1, 2, n. Given by yi equals to some constant alpha plus beta xi minus x bar plus ei. So where, of course, x bar is the sample mean for the observed sample, and E1, E2, all these En, so they are IID and follows normal distribution 0 sigma square. Okay. And now this alpha and beta are constants. So there are three kind of unknowns. So one is alpha, one is beta, and there is sigma. Now please observe that. So note, from here we can immediately conclude the following. So what is E of yi? So all these are constants. It's alpha plus beta xi minus x bar. So that is E of yi. So that's the expected value of yi. What about variance of yi? So all these are numbers. So the only randomness is for ei, which has a random variable sigma squared. So this is going to be sigma squared. Okay. Also yi, it follows. So it's a normal plus constant. So it follows a normal distribution with mean this one, alpha plus beta, xi minus x bar, and variance sigma squared. Okay. So these are the three observations that we first made. Okay. So here the major assumptions are, so here the real major assumption is this random errors. So these are the error terms. So these are the random error for every observation. So we really assume that they are IID and they are following a normal distribution. Okay. All right. Now, how do you, so the goal now, so first thing, if we really want to work with this model, we have to estimate the three unknown parameters, alpha, beta, and sigma squared. Right? So they mentioned that alpha, beta, and sigma squared. So these three are the unknowns, right? So now, how do you estimate those? I will be using. We now developed a lot of powerful techniques. For example, we now know the maximum likelihood estimator. So let's use it. So let's consider. So assume to estimate alpha, beta, and sigma squared. Assume that the endpoints which are given by little x1, big Y1, little x2, big Y2, little xn, yn follow the model, and let's give it a name. So the model that we wrote here Let's give it a name star. So let's assume that this follow the model star. Okay, so let's compute the maximum likelihood estimation. So MLE for Y1 for this sample, Y1, Y2, Yn is given by, now each of these follow a normal distribution with this mean and variance this one. So let's write this down. Uh, it depends on three parameters, right? So typically we write this as theta. Let me just write it once. And theta in this case, it's alpha, beta, and sigma squared. So that's the three values of theta. So this is going to be product of I from 1 to n, and for a particular one, it's given by 1 over 2 pi sigma squared. So each of these are following the variance sigma squared. And then we have e to the power of minus yi minus, the mean is given by alpha minus beta xi minus x bar squared over 2 sigma squared. So if I simplify this, so it's a product of this bunch of factors. So if I simplify this, it's going to be 1 over 2 pi sigma squared to the n over 2. And then we have e to the power of minus, so 1 over 2 sigma squared. And then we have summation I from 1 to n, yi minus alpha minus beta xi minus x bar squared. So let's see if I have right bracket. So I need another bracket here. No, that's correct. Sorry. This square is here, but then this bracket ends here. The square is with this xi minus x bar square. Okay. Now this is a least square problem. So I mean, you might have seen it in various occasions. So one way to do it is to take the log of, so L of alpha beta sigma squared, which is log of L theta, which is given by, if I take the logarithm, it's n over 2 log of 2 pi sigma square, if I take it in the numerator, and then minus 1 over 2 sigma squared summation I from 1 to n yi minus alpha minus beta xi minus x bar squared. Okay. Now, let's see. I mean, we are trying to maximize this one. So maximizing this L alpha beta sigma squared is same as minimizing. I don't want to work with the negative sign. So minimizing minus L alpha beta sigma squared. And out of that, again, so what is that quantity? So it's minus L alpha beta sigma squared is really the negative of that. So it's n over 2 log of 2 pi sigma squared plus 1 over sigma squared summation I from 1 to n yi minus alpha minus beta xi minus x bar squared. All right. So how do you let's call this with a name. So let's call this one, say, well, first of all, if I'm trying to minimize this with respect to alpha and beta, note that this is a function of sigma squared. right? And this one is also, this is a function of sigma squared alpha and beta. Okay, so let's see. So now if I differentiate this, so let's give it a name. So let's call this one, say, h of alpha beta sigma squared. So I can compute d of h alpha beta sigma squared over d of alpha. So the first term is 0. Second term is, let's see, it becomes 1 over 2 sigma squared, and then it's 2 summation I from 1 to n yi minus alpha minus beta xi minus x bar, and then I'm differentiating with respect to alpha, so I get a negative sign here. Okay. Now, if I want to set that to equal to 0, so h alpha beta sigma squared over alpha equals to 0 would give me this quantity. The summation would be 0. So this is summation, the term, the summation I from 1 to n yi minus alpha minus beta xi minus x bar equals 0. Let's see. Now, beta is a constant, and note that let's when I compute this summation, so what do you have? So I have summation I from 1 to n yi minus n alpha minus 0 equals to 0. Why? Because summation of I from 1 to n xi minus x bar is 0. So very easy to check. So first one is nx bar, and this is nx bar, so it's 0. So this term is 0. So that means what we get is alpha is really sum 1 over n, I from 1 to n, yi. Okay. So the MLE, of alpha is given by alpha hat, where we just write this in the random variable. So it's really y bar. So it's y bar. So that is the alpha hat. First important derivation. By the way, also it can be shown that the second derivative, so we are trying to minimize. So the second derivative of this over alpha 2, when we choose this alpha equals to y bar, is positive. That means it's really a minimum value. Okay, I'll leave it up to you how to show it. Okay, it's just one step. In fact, this is actually bigger than 0 for irrespective of the alpha value. But anyway, okay, so it's really the minimizer for h. So that means so this is something we called h alpha beta sigma square. So that is the maximizer for the log likelihood function. So we got that. Also, now if we can compute d of h alpha beta sigma squared over d of beta, so if I differentiate that with respect to beta, what do we get? So we get the first term here is 0, and this is again 1 over 2 sigma squared, 1 over 2 sigma squared as before. And then we have summation I from 1 to n yi minus alpha minus beta xi minus x bar. And then we have, we differentiate this one, so it's minus xi minus x bar. Okay. This term is repeated. Sorry about crunching it. So it's minus xi minus x bar along with that. Multiplied. So the partial of this with respect to beta equals to 0 really yields, well, so first of all, sigma square will go away. So it's summation I from 1 to n. So the first term is really yi minus alpha, but alpha we are replacing by y bar. That is what we found. So what we have is summation yi minus y bar, and then we are multiplying by that. So which is going to be minus xi minus x bar. So this is the first term. And then the second term plus, let's write another summation. Summation I from 1 to n, there is a beta, and there is xi minus x bar squared. We want that to be 0. Okay. Okay. So let's simplify this. So if I just simplify this, this is going to be beta equals summation I from 1 to n yi minus y bar xi minus x bar over summation I from 1 to n xi minus x bar squared. So this is one way of writing it. I'll write another way. Note that so in this summation, it's just second one is just a simplification of this one. Also, summation I from 1 to n yi minus y bar xi minus x bar. So this is the numerator. So the numerator of this, so the numerator can be written as, oh, well, this is same as summation I from 1 to n yi xi minus x bar, and then the second one y bar is a constant, so it's summation I from 1 to n xi minus x bar, which is 0. We have seen this earlier. So this is really the numerator is xi minus x bar. Okay. So hence the expression for beta, which is this one. So beta. So another expression for beta is just beta equals summation I from 1 to n yi xi minus x bar over summation I from 1 to n xi minus x bar squared. So therefore, what is the MLE for beta? So the MLE of beta is beta hat is will be either using this form with y replaced by big Y, or the other one where y replaced by big Y. So it's either I from 1 to n yi minus y bar, and x is a little x bar over summation I from 1 to n xi minus x bar squared, or I can write this as I from 1 to n big yi little xi minus x bar over summation I from 1 to n xi minus x bar squared. So this is the maximum likelihood estimator for beta. Okay. So therefore, the So the fitted value hence we can write this. By that I mean, remember that we started off with this x, yi, xi and yi. So we can write this as the estimated value of yi is given by alpha hat plus beta hat xi minus x bar. Okay. So this is called the fitted value. Fitted value at the point xi, y. So there is a bunch of xi's, there are corresponding yi's, but if we are using the regression, so this is what we are fitting. Okay. All right. So one more thing. And I can also write the expected value of y, which is equals to alpha hat plus beta hat xi minus y. So this is the expected value. Okay. So this, what we're really writing here is really, so this is E of yi. Okay. So we are computing the E of yi, and that is what we're getting. Okay. And essentially, this is the estimate of E of yi. So let's write this way. So this is the estimator for expected value of yi. Okay, so we have done with this one. So estimations for beta, estimation for alpha. One more thing from here, it may be obvious that so therefore what we have really, we have a nice equation. So this alpha hat is y bar, right? So we can really write this as this equation. So yi hat equals to alpha hat is y bar and beta hat is what we get, xi minus x bar. That means yi hat minus y bar equals beta hat xi minus x bar. So there is a nice symmetrical equation. So the fitted value, which is here or here, that's the estimated value of the E of yi. So that minus y bar, so that's the sample mean. So sample mean is y bar, and then it's given by beta hat xi minus x bar. So there is a nice symmetry, and this is true for every I. Okay, so finally, so now we remember there are three unknowns. One was alpha, one is beta, and one was sigma squared. So let's find sigma squared as the estimator for sigma squared. So finally, so if we compute just the way we did it before, let's see. So finally, if I compute h alpha beta sigma squared over u of sigma squared, then we'll get, for the first term, we'll get this as so if I differentiate n over 2 log of 2 pi sigma square, n over 2 over 2 pi sigma square, and then there's 2 pi, so 2 pi and 2 pi cancels, so it's n over 2 over sigma square, right? So the first term becomes n over 2 over sigma squared. And the second term, so when I differentiate that with respect to sigma square, so sigma square only appears in the denominator. So it becomes minus summation I from 1 to n yi minus alpha minus beta xi minus x bar square. I think my square is in the wrong place for the previous quiz. I think I was right in the okay. So this whole thing got to be squared, right? So when you're taking, so this is whole thing squared. So I have a square right here, and then I have a square right here. So the whole thing squared. Okay. So it was not that dominant before, but now it will be useful. Let's see if any other places I made the mistake. No, so that's pretty much it. So if you're computing this thing, so this is the, let me just correct it here one more time. So it's yi minus beta xi minus x bar, and then we take the square here. Much better. Then this bracket is for this one. Okay, so this is fine, and this one is the same thing that I mentioned. Right. Okay. So this is the quantity, right? And then since we are differentiating with respect to sigma squared, so it's 2 sigma squared squared. Okay. So set that equal to 0 to get sigma squared hat equals 1 over n. Set that equal to 0 to get 1 over n summation I from 1 to n yi minus alpha minus beta xi minus x bar squared, and hence the maximum likelihood estimator of sigma squared is sigma hat squared, and where I'm replacing everything by hat, so this becomes a random variable yi, this becomes alpha hat minus beta hat xi minus x bar squared. So this is the maximum likelihood estimator for sigma squared. Of course, we can check that. Yeah. So this is actually the minimizer. So we can check that. For example, I think I wrote it once, and here also you can show that it can be shown that. So it can be shown that the second derivative beta sigma squared beta squared at this value beta is positive. So it's a minimizer. Remember that H minimizer means L maximizer, and therefore we're done. And here we have the same thing. So also it can be shown that the second derivative of H alpha beta sigma squared d sigma squared squared at the point sigma square, where sigma square equals to this one to n x bars squared is positive. So it is minimizer for H, which is maximizer for L. Okay. The log likelihood function. Okay. All right. So what we found is we found all the sort of all the estimators. Okay, so let's just summarize what we just have. So summary is the fitted value at the point xi, yi is given by yi hat equals alpha hat plus beta hat xi minus x bar, where alpha hat is y bar and beta hat equals I from 1 to n. Why? I'll write just one version. We have already seen that before. So these are the values of alpha hat and beta hat. Okay. Now, one more thing. So remember that what is this yi hat? So that's the fitted value. And what's the actual model that we used? So the model was um, yi equals to alpha plus beta xi minus x bar plus ei. And then ei, where IIDs follows normal 0 sigma squared. We just also found the estimator for sigma squared, which is 1 over n, I from 1 to n, yi minus alpha hat minus beta hat, xi minus x bar squared. So that's the second thing that we did. And finally, I'll define one more thing. So this is called the residual. So for this particular model, so we are making some error, right? So there is an actual value, there is a predicted value. So the residual at the point xi, yi is given by ei hat equals yi minus yi hat. So this is the observed value, and this is the fitted value by the model. So that's called the residual. Okay. So these are the three important things, and we are just summarizing this. Okay. Now let's try to understand this alpha hat, beta hat, and sigma hat a little bit more. So let's do that, and then finally we'll conclude with an example. So that's pretty much it. So let's now see what we can do with that. The first result that I'll be showing is a theorem. It goes like this. Under the assumptions that we are working with, alpha hat follows normal alpha sigma squared over n. Okay. So proof. Well, first of all, we have seen that alpha hat is y bar. And what is y bar? So y bar is a summation of 1 over n, I from 1 to n, yi, where yi's are, we have written this in the very second page. Yi's are IID, and yi follows normal. So they follow a normal distribution with alpha, which is the exact value of alpha, xi minus x bar sigma squared. Okay. Therefore, what is, so that means, I mean, if alpha hat is this one, so that means, and it's a sum of the normal, so that means alpha hat follows normal. That's for sure, because it's a sum of independent normal distributions. What is the expected value? So E of alpha hat is given by 1 over n summation I from 1 to n E of yi. And E of yi is this one. So it's 1 over n summation I from 1 to n. So it's alpha plus beta xi minus x bar. So it's 1 over n alpha plus this is going to be beta summation I from 1 to n xi minus x bar, which is 0. So it's alpha. So its expected value of alpha hat is alpha. And what is the variance of alpha hat? So it's again the variance of it's a 1 over, it's a variance of y bar. And it's basically, so the sample variance is the population variance, so variance of yi over n, and variance of yi was sigma squared. That. Hence, alpha hat follows a normal distribution with alpha sigma squared over n. Remember, alpha and sigma squared are the true parameters. Alpha hat is the estimated parameter. Okay, next theorem. So theorem for the beta hat. So beta hat follows a normal distribution with mean beta and variance sigma squared, summation I from 1 to n xi minus x bar squared. All right, so what is the formulation for beta hat? So we have already summarized it in the last page. So here is the expression for beta hat, which is this one, right? So let's see if I look at this structure. So it's basically the sum of independent normal distributions over a number. So it got to be normal, right? So here's a proof. Beta hat is really summation I from 1 to n xi minus x bar yi. I'm writing yi later. I from 1 to n xi minus x bar squared. So it's basically a linear combination of independent normal random variable yi. So here are a bunch of normal independent random variables yi. We are making a linear combination. So it got to be normal, right? So the first thing is beta hat follows some normal distribution. The question is, what's the expected value? Now, expected value of beta hat is essentially 1 over summation I from 1 to n xi minus x bar squared, summation I from 1 to n x, it's E of xi minus x bar yi. Now, yi's we have seen. So that's the second thing, I mean, that's the first time we wrote. So yi's follow a normal distribution with alpha plus beta xi minus x bar and sigma squared, right? So that's something known. Therefore, and here also these numbers, they're not really random. So it's a lowercase, so that means they're given values. Xi minus x bar squared. So these are given values. So I can pull it out. So basically xi minus x bar e of yi, and which is right here. So I can write this as 1 over summation I from 1 to n xi minus x bar squared. And this quantity is going to be summation I from 1 to n xi minus x bar, and this is alpha plus beta xi minus x bar. So this is nothing but e of y bar, e of y. And if I simplify this, so it's going to be, well, alpha summation I from 1 to n xi minus x bar, which is again 0, plus beta summation I from 1 to n xi minus x bar squared over summation I from 1 to n xi minus x bar squared. So that means you see it's beta. The first term cancels and second term is beta. So E of beta bar is 0. Okay. Also, variance of beta hat is really, so beta hat is given by this quantity. So I have to take this one out. So it's square of this one. So it's 1 over summation I from 1 to n xi minus x bar squared, and then the whole thing squared. And then I have to take the variance of this one. So it's summation I from 1 to n xi minus x bar squared variance of yi. So from the simple property of the variance, because yi's are independent. And this is sigma squared. So this is sigma squared. So it's really sigma squared. If I pull it out, it becomes sigma squared over, and then this and this cancels. So summation I from 1 to n x. So there is a this squared, and then just a singleton this. So it's xi minus x bar squared. Okay. So hence we found that beta hat follows a normal distribution with mean beta and variance sigma squared I from 1 to n xi minus x bar squared. Done. So that's the second result. Now, third result, and this one will be little hand waving. Will not prove it that much. Theorem. What about for sigma hat squared? So we'll have sigma hat squared n times sigma hat squared over sigma squared. They follow chi squared with degrees of freedom n minus 2. All right. So basically, here is a sketch of proof. We'll not prove it completely. We'll just have a sketch. So show that and try it. There's a good homework exercise that if I compute this, I from 1 to n yi minus alpha minus beta xi minus x bar squared, that can be written as n times alpha hat minus alpha squared plus beta hat minus beta squared summation I from 1 to n xi minus x bar squared plus summation I from 1 to n yi minus y hat squared, where, by the way, by y hat I mean the so this quantity, it's yi hat, where yi hat, this quantity, is really alpha hat plus beta hat xi minus x bar. I'll leave it up to you to yi. Sorry about that. So this is plus I from 1 to n yi minus yi hat squared. So this is the quantity. And then this yi hat is something like this. Okay. Now, if we divide both sides by sigma squared, so what do you have? So that means if I divide both sides by sigma squared, so I'll have summation I from 1 to n yi minus alpha minus beta xi minus x bar squared over sigma squared. That's going to be n times alpha hat minus alpha squared over sigma squared plus beta hat minus beta squared summation I from 1 to n xi minus x bar squared over sigma squared, and then the third term plus I from 1 to n yi minus yi hat squared over sigma squared. Okay, just rewrite a little bit the right hand side. So I write this as alpha hat minus alpha squared over sigma squared over n plus beta hat minus beta squared over sigma squared over this sum plus the last term. So this yi minus yi hat. So if you just look at this one, so if you look at the expression for sigma squared that we derived at the very end, so look at the expression for sigma hat squared. So it's yi minus yi hat, right? So this is really yi hat, right? So yi hat is alpha hat plus beta hat xi minus x bar. Okay. So that means this quantity, it's really n times sigma hat squared, right? So this is nothing but n times sigma hat squared, the last term here, this one, over sigma squared, right? So let's write this one, since I wrote everything, let me just write the first one as well. And it's beta xi minus x bar squared over sigma squared. So this is the relation that we derived. Now, first of all, what kind of distribution does it follow? So this is the sum of independent normal distributions, right? So this is, this quantity got to be chi squared n, right? What about this one? So it's one variable, so it's chi squared 1. Okay. Now this beta hat also has the, we have already proved by theorem 2, this is chi squared 1. Now, it is so here's a hand waving that, so here is chi square n, this is chi square 1, chi square 2. So it's hopefully it will be chi square n minus 2, and that is, we'll not prove it because we'll not be proving that alpha hat, beta hat, these are independent, right? So we'll simply write it. So it can be shown. That's why I wrote it as a sketch of proof. It can be shown from here that n sigma hat squared over sigma squared, it really follows chi square n minus 2. And also that alpha hat, beta hat, and sigma hat squared are mutually independent. Yes. So that is pretty much it. So now we have developed a very nice way of understanding all the three unknowns. Now with this, let me just finally write a couple of more results, and that is it. So here, at this point, I'm ready to write the confidence intervals for alpha and beta. Okay. The first one is a result. So let's write this as a theorem. For parameter beta, 1 minus alpha, 100% confidence. So that means significance level is alpha. Confidence interval is given by beta hat plus or minus t of alpha over 2 n minus 2 and then square root of n sigma hat n minus 2 I from 1 to n xi minus x bar squared. I'll not prove it. I'll just leave it here. Now there is another way of writing this. I think since we have studied the ANOVA already, we can write this in the following way. So in the so another notation, let me just use it here. So side. So remember that the sigma hat squared. So the way we wrote the sigma hat squared is really 1 over n summation I from 1 to n yi minus yi hat squared, right? So that means n sigma hat squared is the sum of squares for the errors. If I divide, so it can be shown that SSE has degrees of freedom equals to n minus 2. So therefore, MSE, if you recall from the ANOVA, so that is SSE by the degrees of freedom, which is SSE over n minus 2, right? So I can write this n sigma hat squared over n minus 2 is MSE. Right? So that means I can write this simply. So this n sigma hat squared over n minus 2, that is nothing but MSE. So that means it's another way or equivalently. So this is given by beta hat plus or minus t alpha over 2 n minus 2 square root of MSE over this summation xi minus x bar squared I from 1 to n. Okay. So that's another way of understanding the confidence interval for beta. Okay. Finally, as you can imagine, the last one should be for the alpha. So here is the theorem for the confidence interval for alpha. So theorem for parameter alpha, the 1 minus alpha 100% confidence interval is given by alpha hat plus or minus t of alpha over 2 n minus 2, and then sigma hat squared over n minus 2. Or equivalently, alpha hat plus or minus t of alpha over 2 n minus 2. This is MSE over n. So once again, so this MSE is this one. So note that. So we have seen MSE equals n sigma hat squared over n minus 2. Written right here. All right, so these are the confidence intervals for alpha and beta. So this is actually a very, very important way of understanding the regression, a very powerful way. So let's do a couple of examples very quickly. So the first example is the following table shows X, the catches of some fish, and Y, the price of fish meal for 14 years. So here are so first we have the price, and then we have the first year, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay. So first let's write the price. It's 190, 160. So 190, 160, 134, 129, 172, 197, 167, 239, 542, 372, 245, 376, 454, and 410. So these are the prices. It's 410. Okay. And what are the catches? So the catches are actually in millions of metric ton. Okay, in some unit. Some unit. I'll not write the unit. That's why you'll see fractional number. So here it's a 7.23, 8.53, 9.82, 10.26, 8.96, 12.27, 10.28, 4.45, 1.87, 4.00, 3.30, 4.30, 0.80, 0.50. Yeah. The question is, find a 95% confidence interval for beta, for the regression parameter betas. Okay. So let's do that. So here is a solution. So, and how do you compute this? So regression 95% confidence interval will be alpha equals to 0.05, and then we have to compute this one, right? So for this data set, well, so first of all, we can compute the value of beta hat, which is given by summation I from 1 to n yi xi minus x bar summation I from 1 to n xi minus x bar squared. So basically, you can compute this quantity from the given value, and you can find this is minus 29.402. Not only that, so you can find that this quantity, so here n is 14, and therefore, if I want to compute, say, n times I from 1 to n yi minus yi hat, by the way, so we have the so we can compute the mean. So we can easily compute the mean, and we can compute the other quantities. For instance, if I want to compute, say, let's do one of those computations. So let's compute summation I from 1 to 14 xi minus x bar squared. If I compute that, it will be 198.7453. Okay. And based on this one, if I now compute the value of the n times n minus 2 sigma hat squared, which is the MSE. So MSE is given by this one, so it is really n times n minus 2, and sigma hat squared is 1 over n summation I minus 1 to n. So it's yi minus alpha hat minus beta hat xi minus x bar. And you can, of course, compute alpha hat as the y bar from the data. So you can substitute everything here, and you can compute this MSE to be 5139. And hence we are done. So basically, so therefore, a 95% confidence interval for beta is given by beta hat. So we have written it last time. It's beta hat plus or minus t of alpha over 2 n minus 2 square root of MSE over summation I from 1 to 14 in this case, xi minus x bar squared, right? Which is really minus 29.402 plus t of, so this is going to be 0.025. So alpha is really 0.05. So alpha over 2 is 0.025. 95% confidence interval means alpha is 0.05, right? And this is going to be 12. And then we have all these numbers. So MSE is, we found this is 5139. And this is something we found 198.7453. So this is, if you compute, it's minus 40.4822 minus 18.32. Okay. What does it mean? So it means that well, it is what it is. So 95% confidence interval for beta. So, and beta is actually, if you recall, so that is the slope of that x value, slope of that straight line. So what we are really getting is that is, we can 95% confident that the average price of the fish meal decreases between 18.322 and $40.482 per ton for every 1 unit increase of the fish. So that is that's the conclusion, but that is what it is. Okay. Finally, we'll conclude with the last example. Example. Find a 95% confidence interval for alpha. So last time we had the last problem. For the last problem, we computed the confidence interval for beta, but now let's do it for alpha. Okay. So here is the solution. So the 95% confidence interval for alpha will be given by alpha hat plus or minus t of alpha over 2 n minus 2 MSE over n. Right. So alpha hat, which is right last time. So alpha hat is right, really very easy to compute. So it's y bar for this one. So there are a bunch of values of y, which is given. By the way, I'm thinking of so here my variables a little different. So I'm thinking of these prices as the y variables, and these are the x variables. Okay. All right, so let's compute. So here we have y variable, y bar is given by, if you compute this, it's 270.5. So here alpha bar, alpha hat is given by y bar, which is something we have already known. It's 270.5. So alpha, so the interval is given by 270.5 plus or minus t of 0.02512 times 51. We have already obtained this number. So 5139 over n, which is 14. By the way, this number, I didn't write it last time. So, but this is really 2.179. So it's 2.179. So if you compute this, so this is 270.5 plus or minus 41.75. So this is really, the interval is 228.75 and 312.25. Okay. So that's the 95% confidence interval for the parameter values alpha. So this is typically how the parameter values are approximated using the linear regression. So that is pretty much it for this section. I think next time I'll be continuing with this topic a little bit. So we'll be doing one or two more problems. But then in the final class, that is the last time, that's the next time. So what we'll be doing is we'll be discussing a little bit more problems on this confidence interval built on this alpha values and beta values. And finally, we'll be studying a little more topic, okay, a little more advanced topic, and that would be all about this course. Okay? So thank you very much. Please note that I forgot to mention for the last problem. So my x and y's are swapped. So meaning that, let me just mention it one more time. So here, so the first variables are actually y, and the second variables are x. Okay, so this is catches are x, prices are y. Because if it's the other way around, your procedure will be very similar, but you have to do the computation a little differently. So the way I did the computation, I assume this x values, so the catch values are x values and price values are the y values. Okay. All right. So thank you very much, and I'll see you in the next lecture.